Hello and welcome to session number 13. In today's session we're going to be looking at our first compound device. We're actually going to put two different materials together. In this case, a metal and a semiconductor. And that is called either the metal semiconductor junction, or after the first person who exhaustively explored this, it's called the Schottky junction. So this is a cause to celebrate, and what better way to celebrate than starting off with the wonderful music of Jock Offenbach, Can Can. So see you in about 2 minutes. Okay, this is a broad outline of some of the topics we'll be covering today. First, we'll be looking at energy band diagrams of semiconductors, single component semiconductors, both in equilibrium and non-equilibrium. And there'll be about, 9 or so. A couple of them will be a little bit new, and they should be fun. And then we'll be looking at equilibrium in multi-component systems. Multi-component is two or more. And the first one we'll be looking at is something called the Schottky barrier, where we put a metal in contact with a semiconductor. The two most important semiconductors for Schottky barriers are silicon and gallium arsenide. We'll be focusing in more or less on silicon. We'll talk a little bit about Schottky barriers with gallium arsenide way back or in the future. I think that's the last chapter, when we'll be talking about something called a MESFET. Okay, so, and also we're going to start off with N-type silicon. So the first multi-component system we'll be talking about is metal in contact with N-type, N-doped silicon. And then we'll be talking about what happens at the junction when the metal meets semiconductor. The junction is called the metallurgical junction. That's the point of contact, and we'll find that some really interesting things happen, and we'll have to look at some new concepts in order to understand that. So that should be kind of fun. And then if we have time, we'll be talking with P-type silicon. First we'll be talking about N-type in the first couple of parts of this discussion, and then we'll end up with P-type, and then we're looking at a video clip of a the wonderful aria from Rossini's Cinderella, like Cenerentola. Okay, so let's get started with the energy band diagrams. First row, pretty simple, all in equilibrium. We know they're in equilibrium because the Fermi level is straight and horizontal in all cases. So the first one, conduction band on top, valence band on bottom, looks to me like this is just a little bit above intrinsic, a little bit above the midpoint. So I would say that this is lightly doped, probably very lightly doped, N-type. Second one is moderately to heavily doped P-type. And the third one looks to me like this is right smack dab in the middle. So I would say that that is intrinsic silicon, for example. Okay. Now the second row, starting with the fourth energy band diagram, the Fermi level is tilted. So in this case, we would say we were not in equilibrium. Now we're going to talk about this in some detail a little bit later on when we talk about non-equilibrium in multi-component systems. But for now, and we discussed this just a little bit, but I'll just repeat it here and we'll talk about it, like I say, in somewhat more detail. The left side is lower than the right side, which means for the energy band diagram that the left side is positive with respect to the right side. The electric field, therefore, goes from left to right. A hole would be moving from left to right. An electron would be moving from right to left. In this particular case, there is a hole current, even though the material is doped N-type, just very slightly N-typed. There is a drift current going from left to right in the positive direction because the electric field goes from left to right in the positive direction. The current is positive, holes move from left to right. Here we have the right side is positive. The electric field therefore goes from right to left in the negative direction. We have a hole current. In this case it's moderately doped P-type, and we have a negative current going from right to left. In this case, this is the old hot plate experiment. We have the right side is more or less intrinsic. Actually, it looks like it's a little P-doped here, so that's probably a mistake. This should be in the middle. So this is intrinsic, and this is N-type on the left. Here we're in equilibrium. There is a drift current going from left to right in the positive direction. However, there's also an electron diffusion current going also from left to right because there are more electrons on the left side than there are on the right side, and therefore electrons move to left to right, which means the diffusion current moves from right to left, exactly canceling out the drift current, which moves from left to right. I hope I said that right, and I think that's pretty reasonable, but it's a little bit confusing at times. Hopefully not too bad. Okay, the last three are really odd, and the first one is one I'd like to talk about a little bit more detail. These I'll leave for you. These are so crazy that just think about some ways which you can think about what's going on here. I'm not even going to say whether these are realizable. I don't think they are, by the way, but that's just my opinion. So you can have fun with these. I usually give these as exercises just to get people to think about what's going on. This one, however, is real. This is the real deal. What's happening here? First of all, it's in equilibrium. Fermi level is straight and horizontal. However, the band gap changes. Well, we know that the band gap is a function only of the material. Notice the band gap is high on the left side and lower on the right side. So what it means is that the material is somehow changing. We have different material on the left than we do on the right. And that is quite interesting, and we'll see cases in where that is indeed a reality. That's exactly what happens. So this is a big deal, and it's real. These are really way out and kind of crazy, but just take a look at them and see if you can get some feel for them. Okay, so now let's talk about equilibrium in multi-component systems. Again, equilibrium, nothing's flowing. The Fermi level is straight and horizontal. So what I'm going to claim is, to have equilibrium, we need to have flows. We can have flows from left to right. We have two systems, multi-component. This is system 1. This is system 2. We bring them together. We can have flows from 1 to 2, but those flows must be counterbalanced precisely by an equal and opposite flow from 2 to 1. So anything that flows from 1 to 2 must be balanced by the same flow from 2 to 1, so there is no net flow. So if we bring the two structures together, we can have charge transfer, but that charge transfer must be equal and opposite, and that is why the two arrows are in opposite directions, and they have approximately the same lengths. So let's look at what happens when we have flow from 1 to 2. We have the Fermi level, or I should say the Fermi function, which tells us what's the probability for an electron to be in state 1. How many electrons do we have here? So that is given by the Fermi function. G is the number of electrons in state 1. And in order for flow to occur from state 1 to state 2, we must have an empty state in system 2. This is the probability that we have no electron in system, or the component 2. This is the number of states in component 2. So all this part says here that there are probability of having an empty state in component 2, and the number of states in component 2. So to have flow from 1 to 2, we have to have high probability of states in component 1, and the number of states in component 1 must be finite. Okay, now for flow between 2 to 1, we exactly have the opposite. So wherever we have a 1, we have a 2 from 2 to 1. So it's the same deal. In order to have flow from 2 to 1, we have to have a high probability of states being occupied in component 2. We have to have a lot of states in component 2. We have to have no states in component 1, and we have to have a lot of states in component 1, but not occupied. So we just equate these two, set one equal to the other, cancel out the G1, G2. The only way for this to be equal is for FD1 to be equal to FD2. In other words, the Fermi levels must be congruent in order to have equilibrium between components of a multi-component system. Okay, and that's kind of something we would have guessed. Think, for example, salt. You have one side you have salt water, the other side you have pure water. You put them together, the salt flows from the hot part with the salt water to the part which doesn't have any salt water, such that the chemical potentials in that case equilibrate, and we have equal amounts of salt water in both the left and the right side. Okay, so let's talk now about the metal semiconductor or Schottky barrier. And that's the first thing that we'll be talking about. This is the device structure tree. The Schottky barrier occupies a rather central position because from the Schottky barrier we're going to make we're going to make modifications, and each modification will take us to a different structure. The modifications are in green, and if we replace the metal with a semiconductor, we get a PN junction. If we add a second junction, we get two junctions, bipolar junction transistor, or BJT. If the other side, we insert between the metal and the semiconductor a dielectric, we get a metal oxide semiconductor. Generally, an oxide is silicon dioxide or glass. And then if we add source and contact drains, we get the most important device, which is the MOS, metal oxide semiconductor field effect transistor. There are then 5 basic structures. The Schottky is 1, PN junction 2, then we'll look at bipolar 3, then we'll go to MOS 4, and we'll end with the MOSFET 5. And in each structure we are going to have 3 chapters. First chapter is in equilibrium, which will be starting today for the MS, for the metal semiconductor, and then non-equilibrium, where we put in voltages, and then the third chapter is where we do some worked problems. The equilibrium part of it means that it's just sitting there as a structure. Nothing's flowing. Fermi level is straight and horizontal. Okay, so now let's look at the metal semiconductor. We have metal on the left, silicon on the right. It's actually going to be N silicon. That's the one we're going to start with. We put them together, we form a junction, and right at the junction, all kinds of fascinating things happen. So any structure on the device structure tree can be understood, as we say, this is a repetition of what I said before, as a modification of the metal semiconductor diode or junction or Schottky barrier. They're all the same thing. Okay, so let's now look at the energy band diagram for a metal semiconductor structure. Now you'll notice there's a new level called E0 and 2 new terms. One is called psi and the other is called xi. So psi is called the work function and xi is called the infinity, and this new level E0 is called the level in which, or I should say, explains the level in which the electron is completely free of the structure. Now this goes back to the Einstein theory, I believe it was 1905. He happened to shine light on metals, and he found that if the energy was high enough, the electron could basically leave the metal and fly off into free space. And that energy is called the work function of the metal. Psi is called the work function. M in this case is the metal. We have work functions for silicon, that's why we have an S here, and xi is the distance between the conduction band and this new free energy level E0. The important thing is phi sub s is a function of the Fermi level. If the Fermi level rises, the work function decreases. But xi, because it's between the conduction band edge and the free electron energy level, does not change. It is a constant for a given material. For silicon, for example, it is 4.05 eV, where we can't make that statement for the work function. The work function will probably, in fact, it will almost always be more than 4.5 eV, but it depends on the level of the Fermi function. So now we bring these two bad boys together, and this is exactly what we would expect. They're not. Are they in equilibrium? You bet they're not, because the Fermi functions are not congruent. So what's going to happen is this guy's either going to fall, or this guy's going to rise, or this guy will fall and this guy will rise. Actually, we're going to keep this constant. It doesn't really matter. We can keep this constant and let the Fermi function of the metal rise. And let's see what happens when that phenomenon takes place. What happens is that you can see the Fermi level rising, and as the Fermi level rises, electrons fall from the conduction band into the metal. They actually get transferred from the silicon to the metal. And when that happens, the conduction band bends up and the free electron level bands up, and there is a region formed with band bending. In this case, the electric field is from right to left, which would move holes from right to left, and it would tend to oppose electrons moving from right to left. In fact, electrons for the electrically phenomena would want to move from left to right. However, that can't happen because the Fermi levels are still not equilibrated. So we continue, and we continue until the Fermi level on the metal is equal or congruent with the Fermi level in the silicon. Now what happens in this region, and this is absolutely critical, as the electrons are transferred from the silicon to the metal, we uncover the ions that were in this region. This region is, because it's N-typed, we know it's N-typed because the Fermi level is close to the conduction band. The ions, the phosphorus atoms, which have been ionized, have donated electrons, and they are positive. And that is shown here. Positive ions in this region, and negative electrons at the metal surface. There are no electrons, there's no field, I should say, in the metal, because the metal is considered a perfect conductor. However, there is a field in the region right here, because there are fixed positive ions on the right side and electrons at the surface. Okay, so let's take a deep breath, take a step back, and summarize where we've been. So if you go back to figure 815, just someplace here, oh, here it is, we see that there is this new level that we introduce called E0. And why do we need it? We need it because metals have no conduction band edge, no valence band edge, and no intrinsic. They just have a work function. That's the amount of energy that it takes to free an electron from the surface of the metal and basically, boom, kick it out into free space. So we need to, if we're going to compare apples to apples, we need to have this energy level, E0, free energy level, for the silicon as well. We didn't need it before. We will not need it, interesting, not interesting, I think, logically enough, when we talk about the p-n junction, because the p-n junction has no metal. But whenever we talk about something which does have a metal oxide semiconductor, metal oxide semiconductor, field effect transistor, and of course the Schottky barrier, we will always have to use E0. The work function for the metal is a function only of the metal. It is a constant of the metal. Each metal has its own work function. The work function for the silicon, however, depends on the level of the Fermi level. Fermi level is high towards EC, then the work function goes down. The thing that is constant in a semiconductor is the distance between the conduction band and the free electron energy level E0. For silicon, it's about 4. For most semiconductors, it's also about 4. For insulators, just as a aside, like SiO2, glass, quartz, the energy band gap is huge, about 9 between the energy between the conduction band and the valence band, but the affinity is quite low. It's, I think, about, I have to look it up, it's about 2 or 3 eV. Okay, good. Now when we bring the two levels or the two materials together, the Fermi levels must coincide. They must become congruent because the Fermi level of the structure is straight and horizontal. So somehow this E sub F has got to move up. E sub Fm moves up. E sub Fs moves down. Or they both move and they somehow come together. And that's a big deal. And when that happens, electrons are transferred from the surface. I should say, this is the junction. This line right here, kind of an imaginary line. This is the metallurgical junction. So the surface of the silicon is right here. The surface of the metal is right here. Electrons are transferred. Of course, where are the electrons? They're in the conduction band. They're transferred from the conduction band of the semiconductor into the metal. Even though there are a lot less of these guys in the semiconductor than there are in the metal. So why don't electrons go from the metal to the semiconductor? Energy. It's the same thing like if you have let's say a bathtub of hot water, and you take cold water and you above it, and you pour the cold water into the hot bathtub, the water goes down. It's energy driven. So this particular motion of electrons from silicon into the metal is driven by energy. It's not driven by diffusion. If it was diffusion, then the electrons would go from the metal to the semiconductor because there's more of them, but that's not what happens. What happens is that electrons go from the semiconductor into the metal. Now you might ask the question, what happens if the work function phi sub m is less than phi sub f? In other words, if the Fermi level for the metal was up here, well, then electrons would go from the metal into the semiconductor, and that's an important case, actually. We're going to talk about that perhaps a little bit later. Okay, next factoid. The electron transfer at the junction from silicon to metal, going from higher energy to low energy, and the silicon near the surface becomes depleted of electrons. The electrons here that were covering all the positive fixed ions leave. What does it leave behind? Fixed ions. So, where is that? Oh, okay, sorry. It's over here. So these are the fixed ions that used to be covered with mobile electrons, but now they're not covered anymore. In fact, the surface is pretty much intrinsic. So we have a field. The field, whenever we have positive fixed ions and negative fixed charge, and the electrons on the metal surface, they can't move. They can't move out of the metal surface. So we have a field, and we have a field pointing from positive to negative. If we have a field, we have band bending, and that's exactly what we're showing here. We have a field from right to left, positive to negative, which would force electrons to move from left to right, but it's not big enough yet to overcome the, I should say, what's the word I'm looking for the desire for electrons to flow from the surface of the silicon into the metal. That is the overriding concern until the Fermi levels are equilibrated. At that point, everything stops and the band bending becomes its fixed value, its maximum. We can see the bands are bent here. If the bands are bent, there's a field. If there's a field, there is a voltage. So we have an interesting situation. We have, for the first time, a source of energy, if you will, inside of the silicon. Right here, this is the silicon. This is the metallurgical junction. Right here, this is the silicon. We have a source of energy. So you say, why can't we use that? And that source of energy, by the way, depends only on the structure, only on the doping. So it would seem like we have a perpetual motion machine. It works out, and we'll make some comments about that in the future. Either that or it's in the text. I write about that a little bit. We can't use that, so unfortunately we can't make a perpetual motion machine. Oh, darn. Oh, well. Anyway. But the bottom line is, when the process is complete, what do we mean by complete? The Fermi levels of the metal and the silicon become congruent. That is the point, or coincident, whatever one wants to use. Equilibrium is established, and now there is one Fermi level for the entire structure, and it is straight, and it is continuous, and it is horizontal. So that's the big deal. Okay, let's look at this a little bit more carefully. We'll notice that there are two important numbers here. One is called phi Bn. B means barrier. N means that, well, this is going to be fixed. Phi Bi refers to the fact that there is a barrier in the silicon. This is the barrier in the metal. Actually, I should call it phi Bm, but for some reason they call it phi Bn. I'm not quite sure why. This is the barrier for electrons moving from the silicon into the metal, and it is significant. It can be rather large percentages or fractions of a volt, 0.2 volts, 0.3 volts, I should say electron volts, but it's a significant number. And of course W again is this region which is essentially depleted of charge. It probably would have a charge density of on the order of 10 to the 10th. So when equilibrium has been established, Fermi levels are congruent, the depletion region W has reached its ultimate value, and it depends on the doping of the silicon and the difference in the work functions between the metal and the silicon. Okay, so actually there are 4 cases in general. We're going to be only looking at 2, and really 1, but we'll mention the other one. There are 4 because there are 2 for N-type silicon and 2 for P-type silicon. The first case, that's the case we've been talking about. This is the most important of the 4. And in that case, where is it? Oh, up here. The metal work function is greater than the silicon work function. And that's the case where we produce this band bending, and notice that the bands bend up, and I'll just give a little bit of a preview for that. This is a big deal. Whenever we go from this region here, what is it? Don't forget that the horizontal axis is position. This is the surface. This is the interior. The interior is given by a couple of names. It's called the bulk region. It's called the quasi-neutral region. Don't ask me about a quasi-neutral. It should be just neutral. Or it's called the interior. In the quasi-neutral, I'll use that word quasi-neutral even though I don't like it, we have all of these fixed positive ions, if it's N-type doped, which are quote-unquote covered by a sea of electrons. So there's no net charge. This is called the depletion region, has a width W. This is depleted of charge. And you'll notice that in this particular case, the bands bend up. And here's the general rule, and we'll prove it later. Whenever one goes in an N-type silicon, which is hooked up, if you will, to a metal whose work function is higher than the silicon, then the bands will always bend up. And that's a big deal. And I've tried racking my brain to figure out a nice mnemonic to remember that. It's N-up. And nup is not a very good thing. N-U-P, I don't know. It doesn't make a lot of, it's not catchy. You know, like D over mu is KT over Q, it rhymes. I can't think of a nice way to remember that. But the bands in N-silicon will always bend up in at the depletion region. Okay. So the interesting thing about this particular case is we have a barrier, and because we have a barrier, we're going to find that this is what we call a rectifying junction. We can either increase the barrier, and we're going to do that in the next chapter by applying what we call a reverse bias, so the barrier actually grows, or we can decrease the barrier by applying what we call a forward bias. But the important thing is that there is a barrier, and that barrier gives rise to what we call a rectifying junction. Forward bias versus reverse bias. Okay, the other case, and this again we just repeated here because what we said before, the situation is somewhat analogous to connecting a small cup of water to a large reservoir. Even if the large reservoir is hot, it's got lots of energetic water molecules, they're not going to flow up. The water is going to flow from the high. If you have the cup above the water will always flow from the cup into the hot water. Okay. Now let's look at this in a little bit more detail. We want to find a relationship between these two barriers, the phi bi and the phi bn, as functions of the work functions and xi. So that's our task. To derive expressions for the barrier heights, well, this should be phi bn and phi bi, sorry about that. I think you know that. There's two of them as functions of xi and the two work functions. So, first thing we see, just reading right off the figure, it's not very difficult. Phi bn, distance from the conduction band edge in the metal to the Fermi level. And what we do here is, this really doesn't exist, but I should have perhaps, if I was smart, which I'm not, if I was smart I would have made this a dash line, because it really doesn't doesn't exist in practice. So this is fictitious, but it's there anyway. It's just a continuation of the conduction band edge in the silicon. So we see that the work function in the metal is equal to xi, which is the distance between the conduction band edge and E0. It's the same as here. It's just carried over, plus phi bn. So phi bn is equal to phi sub m minus xi. And that's kind of a relatively straightforward expression. Now let's continue. So if we rearrange this, it's the same picture. We're going to rearrange it to produce figure 822. And from figure 822, we see that phi bi is equal to phi sub m minus phi sub s. And you could see that probably by doing what? I would just take this guy and bring him up here. So if you bring this up here, I probably should have put that in. The distance from this, I'm going to extend this line from here to here is the band bending. That's phi bi. So phi bi plus phi sub s is equal to phi sub m. And that's exactly what we have here, that the barrier for electron motion from the silicon into the metal is given by the difference in the work functions. And we see that this guy is constant. It's a function only of the metal. But if phi sub s becomes smaller, then phi sub bi actually becomes larger, which is kind of interesting. And, okay. And also by inspection from 822, we see that phi sub bi is equal to phi sub bn minus this guy right here. This is the difference between the conduction band edge and the Fermi level. So that's equation 821. Again, there's no fancy partial differential equations. It's just reading off these values from the figure. So that's fairly straightforward. Okay, and we should remind ourselves, and this is a big deal, that phi sub m for all this analysis must be greater than phi sub s. If the opposite is true, if phi sub s is greater than phi sub m and electrons are transferred from the metal into the semiconductor, then we have what we call a non-rectifying junction, or even an ohmic junction, and that's the second case. That's basically case 2. Okay. Now in this section, again the 8.5 refers to the section in the text, we add in the intrinsic level. I'm not going to go through this in any detail at all. I'll just let you read it, but the interesting thing is that equation 824, this is perhaps the bottom line. This gives the barrier for electron motion from silicon into the metal. That's the thing we're going to raise up or lower depending on how we apply a external voltage. And it's equal to the metal work function, which is a constant, minus this thing right here, E sub f minus E sub I in this case. And for silicon with actually silicon which has a metal work function, not a metal work function, a silicon work function of 4.05, and this is Eg over 2.55.56. We get this rather interesting number 4.6. So I'll let you read about that because it is not really critical for what we're going to do in the future. Next time, what we will do is to review this all again, maybe make some comments about the about this equation A24 because it's just an interesting equation, and then we'll go on to p-type. So we're not going to start p-type today. So we will end. There it is, from a video clip from Rossini's La Cenerentola Cinderella. We all know the story of Cinderella, the Cinder girl who marries the prince with the golden slipper and the whole thing. Now, in the opera, it follows fairly closely. Cinderella is oppressed by her two stepsisters. They're not very nice. And her stepfather. Did I say stepfather? Yes, because while in the Disney production, I don't know the original story, I've never read that, but in the Disney production, in the story that's come down to us, Cinderella has a wicked stepmother, but this is what they call opera buffo, which means comic opera, and it's very hard to make fun of a woman. That's a fact. So men are, well, I is one, so I know that men are very easy to make fun of, and in the opera, Cinderella has a wicked stepfather who's kind of a clown, and the last aria, when Cinderella finally marries the prince, and she sings this wonderful, wonderful aria to end the opera, Non più mesta. So enjoy, and we'll see you next time.